Swayam Prabha. Digital India. Educated India.
Good morning, welcome you all to the next class in this particular course on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. In the past 3-4 classes we have been talking about the absorption spectroscopy, some basic concepts, basic principles, applications in variety of ways. One last application let us look at in this particular class, that is on the basically on the nanomaterial. Though I have started in the previous class, let us look at more details of that in this particular class. So absorption spectroscopy can be very well used to characterize, to identify whether a particular composite is formed or not formed, that is, which is nothing but the characterization also. And in addition, it can also give certain aspects like the shape, size kind of a parameters. So variety of these things can be obtained, and where these material nanocomposites are used for various applications, we will see a few of them in this particular class before we complete the topic on the absorption spectroscopy. Now let us look at this particular slide, which is on the silver nanoparticles. This is a very well known thing in the last 25-30 years people have been heavily using, but even then the absorption spectra is of very great use. Right? You can make the silver nanoparticles in variety of shapes and variety of sizes as well. So as long as these are in the nanometric scale, and the electrons which are on the surface, basically the conducting kind of electrons, will get sort of influenced by the light that incidents on these particular particles, and there is a collective kind of a oscillations coming out of that, and that results in this kind of a band which is called surface Plassmann resonance. This is an important aspect, surface Plassmann resonance. Okay, so if you have particles of very big size, you would not find because that becomes a bulk. And if you have particles of very tiny size, much lower, then you will not also find this. So you would find for other kind of systems here. So this helps, this SPR, spectral features, which is measured using the UV visible region of the spectrum, helps in understanding the size, the shape, and even the refractive index of the medium, etc. So let's look at this particular slide kindly on this spectra. We have the spectra collected for 10 different types of or sizes of silver nanoparticles, as you can see here, 10 nanometer, 20 nanometer, 30 nanometer, etc., up to about 100 nanometers. Now let us look at the corresponding color code kind of thing. The black, which is the starting one, which is about the 10, then the red one 20, then the green one 30, etc. What is happening? So there is not too much of a difference within these much in the optical density or the intensity of it, but there is a positional shift. And one more, if you see carefully, the width of the band is also increasing. Now as you go further like 40 and 50, then the shifts will be a little bit more dramatic. So the shift in this and the width, all this, so the peak position is shifting quite a well, and also the peak is becoming broadened. Now when you come to this something like 60, even at 50, you can see in this green one there is a little bit of shoulder. The blue you can see very tiny, the green you can see somewhat, which is 50 nanometer, and then when you go to the 60, yes, you can see and when you see 70, you can definitely see. So that means as you increase the size of the nanoparticle, what is happening? Not only the shift in the main band, that is what you notice, additionally there is a new band coming. So the overall band becomes broadened, and see, it is like this, and the next case it is like this, and next case is like this, next case it is like that. So it is the main band is not only shifting, the new band is also forming. So these are the kinds of things that you are seeing, and that's what is basically characteristic of change in the shape and the size of these things. So when you go to the 100 nanometers, you can see one around 400 nanometers PR band, another around 520 nanometer band, which is somewhat a little away from the original, which is 410, not only in the position, but also in the intensity, but also in the width and the shape, all of this. So this is an important useful technique where one can utilize this. So let us look at another example. Even if you have a different kinds of things like plate-like structures, so plates, so the plates, the one which are shown over there are the triangular type, but some of the plates could be somewhat close to the circular kind of things, but the thickness would differ. So in the plates, it is the basically thickness. So the thickness has kind of a reflectance back on the SPR band or the spectrum, absorption spectrum. So because now in the nanomaterial synthesis there is a huge amount of control. A lot of controls are there in order to make the systems to whatever the size you wish to. So in this case, please look at the spectrum, the figure given over here. So one were able to make a variety of thicknesses, and if you look at their suspension of these solutions, you can see the colors are different. Now if you look at their absorption spectra, so obviously they are shifting from here somewhere around 500 to around 600 to around 700 to around 800 to around 900, etc. So you can see that these are, so these are all just because of the change in the thickness of these. So therefore, since we have a good control in making such kind of a compounds, why cannot we make use of these? Where we can make use of these? We can make use of these in photovoltaics, we can make use of this in molecular detections, photothermal therapies, etc., in all these things. So this is another way where the absorption spectrum also helps. Look at some more examples. This is an example. In the recent days, there is a lot of crisis during the COVID pandemic time, to clothes to become quite antibacterial type. So this kind of research helps a lot in making the textiles more antibacterial. So what you do, you make a coating on the textile. So kindly look at the slide, please. So now in this, the zinc oxide and silver based zinc oxide nanoparticles are basically used. You know very well the silver nanoparticles are very good as antibacterial agents. Now you need to coat these onto the surface of the textiles. That's why these materials are used. You can see this GPTMS, and because of this group, then it will open up and then connect it, and then tetra ethyl the silicate, silicate, and then the chitosan. Chitosan is a carbohydrate polymer. So these things, if you take in a proper appropriate mixture, you can make this kind of a polymer. This will hold onto the zinc oxide or silver zinc oxide surface and adhere to the textile, and that will last for long even when you make several washings. So therefore, then your cloth becomes the antibacterial, and this is very important in medical areas, etc. So this can be identified from the absorption spectrum, whether you have been able to coat this one or not. So you look at the spectrum of this separately, spectrum of the chitosan, and spectrum of the zinc oxide and zinc oxide with the chitosan. So you can see this from the band structure and the intensities and the shifts, you can make out, yes, this particular surface is being coated with this particular material that you have a chitosan polymer. This becomes a conjugated kind of a polymer, and that is being used. These are all some more details that we don't need to discuss in this. So you can also have other kinds of things. For example, you have many of the reactions, you have some kind of a radicals, hydrogen peroxide, peroxy-based radicals, and if one were to remove these ones, then you can stop antioxidant kind of a activity. So these are antioxidant kind of a thing. So for this is also referred as the catechol activity. So these are made with the iron complexes and cobalt with the beta cyclodextrin. So beta cyclodextrin complexes of iron 2 and cobalt 2, you take their sulfate, hydrated sulfates of cobalt and iron, and then mix with this beta cyclodextrin and make your complex of this, which will cross link when you add the citric acid. So when you to this mixture you add the citric acid, that will cross link that. And this cross link material is suitable for removing the radical or the peroxide based species, and therefore it acts as an antioxidant kind of thing. So that's what is referred as a catechol activity. So one can find this catechol activity by following the absorption spectra. So you can see that simple phenanthrene complex, the iron with the cyclodextrin and with 1:1 ratio, 3:1 ratio, and then you see that 1:2:1 where you have added the citric acid as well, and further citric acid levels. So you see that these absorption spectral changes, that clearly tells that you're able to remove basically the peroxide based kind of a species. So it acts like a catalase activity, whether it is based on the iron species, whether it is complex, or based on the cobalt complex. So all these things. So of course you can see which one is working better by comparing the spectra here with the comparison spectra. That is not a part of we need to worry about here, but that can be. And then one can select which of the compound can be used for further applications in the process too. Further. Okay, and not only these kind of an applications, you can also look at these in photovoltaics. In photovoltaics, what you see, you often look at the cases where how to monitor the band gaps. So the band gap monitoring can be done by these UV visible absorption spectra. Now here is an example which is shown for the titanium dioxide PANI. PANI is the polyaniline. Polyaniline is synthesized by taking the aniline and electrochemically polymerizing at the electrode. And this is a very well known synthetic polymer, and it has a huge amount of pi system, and then a lot of things can be done with that. So now this is the TiO2. TiO2 obviously will have the band gaps, and you wanted to do the control of the band gap by applying this PANI. The PANI kind of thing. Here is a set of things where the percent of the PANI versus the titanium dioxide. This is 2%, this is 4%, 6%, 8%, 10%, and pure PANI. So without any, that will be a control. So you can look at the absorption spectra very nicely. Absorption spectral are changed, as you can map with this particular color here, pure PANI, and as you go to these ones at different levels of this. So what is happening? Your absorbance spectra at all wavelengths is changing, and of course the peak positions are also changing. So from this you can, using the tau plot, you can convert this by making the tau plots. These are the tau plots from the slope of this, each of this line here, the vertical line here, when it crosses the x-axis, you get the band gap. So these band gap values are, you can see that they change from 3.4, they are shifting from to the 3.34. It's a very considerable change with an increase in the concentration of the TiO2. So as the TiO2 concentration in the nanocomposite increases, so this value is decreasing. So that means you are trying to control the band gap with this. Okay. So this is another application where one can utilize. Let's see, we have any other application? Yes. One can also use in anti-cancer, antibacterial area, and we know very well the silver, and the silver is very well used now. The silver can be modified with this graphene oxide. So it's basically you can take the graphene oxide and put the silver. So you can put the silver on the graphene oxide or graphene oxide kind of a layers in variety of ways. So how would it happen? You take the graphene oxide, you take the silver salt, obviously silver nitrate, and then you take some other agent which will reduce the silver plus to the silver zero. For example, here in this case, it is the walnut green husk extract was taken. There is an extract from the walnut husk, and that particular thing has a lot of polyphenolic kind of a compounds, and those things will reduce the silver plus to the silver 0. Please look at the slide, please. This can be done in two ways. For example, you take graphene oxide and then you put expose it to the extract, the reducing agent. So at the first you take the silver nitrate, then you expose to the reducing agent. In the other case, you take the graphene oxide, expose to the reducing agent, then add the silver nitrate. So there are two ways. So this is, you have your graphene oxide plus this extract, okay, and silver nitrate. So this is shown as the type 2 here, and the silver oxide plus AgNO3, then add to the extract. So this is shown as 1. So you have, in one case, you have the silver nitrate is initially added graphene oxide, then the extract is added for the reduction. In the other case, the graphene oxide is dipped into the extract, then silver nitrate is. In these two, there is a difference in terms of the way that the silver nanoparticles are. In case of one, huge amount of silver nanoparticles are formed on each of these layers. For example, if this is one of the, so you get a huge amount of aggregated spaces. In the other case, you have a very distinct kind of a, so this is in the case 1 and this is in the case 2. So therefore, you have a better surface area, better reactivity, etc. Therefore, the one where you initially take the graphene oxide sheets and expose it to the extract and then add the silver nitrate, that is what is 2 refers to, AgZO2. This has a better antibacterial and anti-cancer activity as compared to the one which is. So how do we make out? You can make out by just comparing the absorption spectrum. This is from the method 1, this is from the method 2. The corresponding one, if you compare, map it 1 to 1, you will be able to find. Both of these are done at 30 minutes, 3 hours, 6 hours, 12 hours, 24 hours. Again, the same thing. Now you take the corresponding one and suppose you take it to 24 hours, this one somewhere here and the 24 hours here. There is a shift, there is a change in the kind of a intensities, etc. All these talks to you about the efficiency of that. 2 is much more efficient than that of the methodology 1. So therefore, when you make these kind of a devices, it's very important how you're doing. So whether you have the reducing agent initially and the silver ions later, or whether you have the silver ions first coated and then the reducing agent later. So these will differ in terms of the making these kind of. So here you get more clusters and then here you get discrete. Okay, that makes a lot of difference in terms of the effect of that. All these can be monitored by absorption spectroscopy. Okay, so we have now looked at a variety of aspects relevant to the absorption spectral thing, very basic principle, how it can be applied to in terms of how one can analyze the spectra in case of the coordination compounds, what kind of a transitions expected, DD ligand based and the charge transfer based, all of these, how their characteristics, what kind of transitions are allowed, what kind of transitions are forbidden, how even the forbidden ones are being allowed, and they are boon in disguise because you can identify the spectra based on you can identify the compounds based on such kind of a spectra. So all of these are we have discussed. Then we looked at a large number of examples of these in analyzing the simple, the complexes by varying the ligand, by varying the geometry, by varying the deconfiguration, all kinds of combinations we have looked at. Then we have looked at even when these are present in some kind of a protein based complexes, also we have looked at, and then how the absorption spectral change. Then we looked at a host of information on the spectrophotometric titrations, which are very vital in this kind of a chemistry where you are trying to identify the complexations, etc. You can get the ratio between the metal ion and the ligand with all those kinds of things. You can get the pKa determination, you can get the stability constants, so everything. So all of those have been demonstrated very well, and in the latest in this particular class I have demonstrated the variety of applications in the arena of the nanomaterials, how the absorption spectra can be utilized. Now let us try to sum up by looking at the following. We need to do a little bit of practice. So I always keep giving towards the end of any particular topic practice sessions. This is another practice session. So this is basically practice session 6, means 6th topic as far as my kind of accounting goes. So you need to look at this. So I will just go through and give you some kind of a feel. You can always work on your own. Let's look at the first one. Assume that you are given 2 vials which contains both are copper 2 complexes. So one of them vial has got a tetrahedral compound, other one is having a octahedral compound. Now using the electronic absorption spectrum alone, only that, how do you identify which one is which? Just explaining is good enough. So I have already covered that. The kinds of absorption intensities that you find, why, etc. You can go back, look into that and try to respond to this. So I gave you a clue. This is based on the intensities. The intensities do vary a lot. That means your epsilon values can be used as a criteria to address this particular problem. Okay, I hope that is clear. Let's go to the next query. Assume that you were given 3 different absorption spectra corresponding one to each of the transition metal complex possessing D1, D2, D3. Please have a look at the slide because I am reading out from here. So that means you are given 3 compounds in 3 vials. One has got a compound with a D1 metal ion, other is a D2, other is a D3. Okay, how do you identify which one is which? So if you explain a general approach is good enough. How do you identify? So you identify from the number of transitions that you have, basically, because we don't need to look at what kind of a ligand is there, assuming that in all the 3 D1, D2, D3 you have the same kind of a ligands. You also assume that same geometry, assume that they are all octahedral. So assuming that the octahedral and the ligands are same, so you compare the D1, D2, D3. So D1, D2 and D3 octahedral same ligands. So if this is the case, everything is boiled down to quite simpler way. So these are all I have already talked to you that you need to get yourself exposed a little bit from the coordination chemistry that you studied earlier, where the Tanabe-Sugano diagrams will help you in number of transitions, etc. So the number of transitions will also help, and the type of the transitions that you have. So all of these are known from the Tanabe-Sugano diagrams. So that's the clue. You can work using that. Hope that clarifies you. But you need to do homework, of course, not work out for you. I've given you the clue and approach for that, and that's how I do it. Go to another one. A biochemist isolated and purified an enzyme of iron 2 plus, so in the laboratory in vitro, and then he performed a reaction to partially exchange iron 2 with a copper 2 plus. That means not completely, partially. So now your task is, how would you know what percent of iron 2 is replaced by copper 2? Only using the absorption spectrum. Okay, so it's again, so you can have a completely iron 2 containing spectrum, completely copper 2 containing spectrum as controls. Now as a mixture, you compare the absorption spectrum of whatever the mixture that he has done with that of this. From this you can quantify how much of iron is still there, how much of copper is still introduced. So just by quantification, by overlaying the spectra and then deconvoluting and then comparing with that. Another problem, a researcher prepared a nanocomposite of zinc oxide and coated with a polymer. I have shown some example towards this particular class and this kind of thing. So having some aromatic groups, so that's the clue, aromatic groups. Now you know that once you say aromatic groups and you say absorption spectrum, obviously you know where the aromatic groups come, starting from 280, 200, 290, 300, 320, 350, depending upon how well and what level of aromaticity that you have all of these. So that means you have a good handle for you as an absorption spectrum. So you have a simple zinc oxide, you look at the absorption spectrum. Now you look at the product which the researcher claims that he has coated. Now you take the absorption spectrum. So you take the absorption spectrum and see whether you have these strong absorptions in the aromatic region with slight shifts, etc. broadened, all those things will be there because they are coated, so you can make out. Okay, so with appropriate controls you can also get roughly a % of the polymer that is coated as well. You can get that as well. Hope that clues is sufficient enough for you to work on it. Okay, another example, you are given two samples of which one is gold nanorods and the other is gold nanospheres. So this is one is nanorods, other is nanospheres. So you have and other is nanospheres. Okay, so you have two different types, two different shapes. Okay, now the clue is already there. There are two different shapes, so therefore you can easily identify from their absorption spectrum, from their SPR, the characteristics of the thing. So you can measure for both the gold nanorods, from gold nanospheres. The reason is that these have got two preferential directions on this side and on this side. So therefore you have two different peaks and broadened, etc. You will find in the spherical you don't see that much of a broadening, and depending upon the size there may be a shift. So using these characteristics you can identify which one is the gold nanorod, which one is the gold nanosphere. Look at some more examples. A researcher performed a titration with a given ligand with a given transition metal ion, any hypothetical, at different concentrations. So you take a ligand, you keep adding different concentrations of the transition metal and find their absorption spectrum. Then you change another pH, again do the same thing, again pH. So at all these conditions he has measured the, so huge amount of the absorption spectral data you have. Explain what all he can derive from such data. Number one, you can derive at one particular pH varying the concentration. You can derive the complexation by varying the pH, how the complexations change, complexation stabilities change. That can also be. You can also get the pKa values at different kinds of pKas. The ligand that is given undergoes some protonation, deprotonation things. So all of these kinds of things can be derived. All these have been covered in different examples in my lectures, so you can use that. Look at another example. An acidified solution of potassium dichromate showed a strong band at 350 nanometer. So explain the origin of this band. So obviously we know that this is coming from the ligand to the charge transfer, that is oxoligand to the charge transfer. So you can further think and work on this. Pyridine shows a strong absorption band around 255 nanometer. Suppose we add some HCl to this, the band disappears. Why? We know that the HCl has the proton adds at the heteroatom and then becomes nitrogen, becomes NH plus. So you have a pyridinium hydrochloride is formed. Pyridinium hydrochloride is formed, therefore that band disappears. So explain why in general. So that means even the reactions can also be found out. Here is a reaction took place. Of course, it's a protonation reaction. Okay, so explain why in general the absorption spectra of Mn2 plus complexes have extremely low absorptivities. I have already explained in the in one other class, maybe a couple of classes, that this the transitions of this deep 5 and these are all even in octahedral, so they are all 5. Mn2 plus is D5, is a high spin, and then you have a Laporte already forbidden, as well as spin is also forbidden, and these are the things that you have looked at. So look at that one last thing that I have asked you to do the practice. Of course, you can do many more things, practice on your own, pick up from the internet and work on it. While the chromium 3 aqua complex exhibits its absorption band around 15,000 centimeter mass, that of a cyano complex exhibits around 25,000. Okay, so both, let us assume octahedral, both have 6 ligands. So you have so chromium H2O6 and then chromium Cn, this is 3 plus, Cn6 3 minus. So this is delta O is 15,000 centimeter inverse, and this delta O is 25,000 or whatever. So 25,000 centimeter inverse. So you know very well that so you have a huge gap coming in case of cyano complex, and we know the cyanide ligand is a strong field ligand which will split the energy difference much greater. So therefore chromium 3 cyano complexes tend to be more into this. So you can easily explain the difference from the ligand field strength of that. So many things. So this is not the end of that, this is the beginning. I am showing you how to do the practice. Kindly go ahead and do a practice to make your understanding on these more robust. You will only know when you do some practice on these things where you understood the subject. Okay. So I think with this I will close for the absorption spectral part of it. Then in the next class you can look forward for the emission spectroscopy or fluorescence spectroscopy. Thank you.